Hi there, welcome back. Welcome to my channel, a little bit about everything. I've been away for a while because I've been busy and I have a little time to myself right now, so I thought I might try my hand at building a centrifugal pump on my 3D printer. I do need one, or sort of like a bilge pump or sub pump for around the shop in case there's spills. I was going to use some food grade pipe or tube. You can get it at either the grocery store or your local hardware store, and I wouldn't need anything but printer to actually make it, right? The definition of a centrifugal pump is it is used to transport fluids by conversion of rotational kinetic energy to the hydrodynamic energy of the fluid flow. If you reverse a centrifugal pump, you're going to get a turbine. Then you would be converting water pressure to mechanical energy. But in this case, I want a pump. So it's the opposite, right? And a little history on the centrifugal pump. The first centrifugal pump was built in the late 1700s, or what we know it as today, by a guy named Denis Papin. He built it using straight impeller vanes. Now the vanes we know today look more like turbine-like. They have a twisted shape. They're not straight vanes, right? And the way a centrifugal pump works is axial flow enters through the eye of the casting. It's caught up in the impeller blades and is whirled tangentially in a tangent fashion and in a radial fashion outwards until it leads through all circumferential parts of the impeller in the diffuser part of the casting. The fluid gains both velocity, pressure while passing through the impeller. So if you gain velocity and pressure, a donut-shaped diffuser or scroll section of the casting decelerates the flow and further increases the pressure. So as the water leaves the blades, it decreases the flow but increases pressure. It is important to note that the water is not pushed radially outwards by centrifugal force, but rather by inertia. Okay? The natural tendency of an object to continue in a straight line when traveling around a circle. So it's not a centrifugal force, but inertia. Encountered, okay, by centrifugal pumps are cavitation, very destructive, wear of the impeller. If the fluid that you're pumping has debris in it that can probably act as like sandpaper as it rubs or passes through the pump, right? That'll wear down the impellers. Corrosion, if you have seawater and your impeller's made out of steel, it is going to rust, right? Overheating. Now pressures, when you pressurize water, you get heat. And there's bearing heat and friction heat along the shaft, right? There are different types of seals that are used on pumps. And some are packing materials. They're cheaper. They work, but you get leakage, but not large amounts of leakage, but they're more economically feasible. So let's say you had something you don't want to leak. You can use what we know as a seal today, right? A rubber seal or plastic seal of sorts. And if another way to seal the pump would be through magnetically coupling the pump. That way there's no axle. There's just an impeller floating around in the pump. And if you magnetically couple it to the motor, as it spins, there's nowhere for the water to leak. And you would use this in applications where a leak is not acceptable, like in a nuclear plant. Designing the pump and bringing it to reality on a 3D printer, and then trying to test it out. Hopefully I'm going to be successful, so let's get on with the build. Well, the job is 30%, 38% finished. I don't know if that's 47 minutes till finish or 47 minutes into the job print. I think I'm printing the casing. I wasn't sure because I didn't label it right. And I decided to print it at 100%. If it was, say, the impeller, I would print it slower because there's going to be tiny little parts that can actually break off or sag. They need time to cool down between layers. But I think this is the casing, and it's the by the looks of it, it's the bottom portion of the casing, or no, it's the top portion. And the way I can tell is that the bottom portion has a extension, which is probably, I'll call it the bearing housing for the impeller shaft. This doesn't have a hole in the center of it, so it's the top of the casing. I'm getting the printer ready for the third print. This print might be the impeller. I'm hoping it is. I've slowed down the feed rate to 90%, which I think it was supposed to take like an hour and some odd minutes. So it's going to take 10% more time to actually complete the job. And this is part of the casing. Right there where my thumb is, that's where the shaft is going to go in, and the shaft's going to be a drill bit, and it's going to hold on to the impeller here, and that is the exhaust of the casing right there. It's part of the casing. I had to do it in two sections because it's the only way I can get the impeller in there, right? And from the looks of it, this circle here where my thumb is, the circle where my thumb is here, going around there, that's the size of the inlet, and the outlet's going to be like, only 20%. So I'm guessing that might cause cavitation, right? Because it's going to restrict the flow. So I might have to redesign this. Well, I was wrong. I guess I'm printing the inlet. What's going to happen is the two casings are going to be glued together, and then the inlet's going to be glued to the casing. But before I do that, I have to make sure I put the impeller in there with its shaft. And it's not going to be it's just a proof of concept. If it was being done for real, you'd have to leave room for packing, bearings, and all sorts of things. Some kind of lubrication for the impeller shaft. Plus, one would have to make the inlet should be equal to the outlet. So if your inlet was 1/2 inch, you'd have to have an outlet that is 1/2 inch, and make your casing accordingly to it. I've started my fourth print, and like I did before, I set it to 90. I don't want it to go too fast. And I've augmented the heat from 50 degrees Celsius to 58. I want good adhesion of the PLA material if it is the impeller, because it's going to be under lots of strain, twisting force and stuff like that. So it has to be sound. I'm hoping this is it. This is my fourth Fourth piece of the puzzle, yeah. Yep, this is the impeller print. Making the impellers. I let the glue dry, or the epoxy, and nothing seems to have glued together. It's functional, and I guess my next test is going to be see if it pumps water. Well, you get to see the first try of the pump. I'm going to put the inlet in the water, and I'm going to spin it on low speed to see what happens, and then I'll try it on high, see if there's a difference. Well, there it's in the water. Now I'm going to check it out to see what happens when I'm on high speed. Oh yeah. That's cavitation. You hear cavitation there. See?